Come back to the second half of this lecture. This time I am going to start a new section on generating systems. Linear independence, and basis. Okay. So, as usual, let V be a vector space over an arbitrary field. K. Definition: a family small vi, I in I, of elements in V is called a generating system for V if every element of V is a k-linear combination of VI's. So that means every x in V we can write as a representation of the form x equal to summation ai vi I in I, and only finitely coefficients are non-zero. So that means in notation from our earlier lectures, this I tuple ai belongs to k power round bracket I. Recall that only those I tuples belong to k power round bracket I for which ai is equal to 0 for almost all I. So that means this sum is really a finite sum. Equivalently, V is kVi. Remember from one of the earlier lecture, this is the notation, the right hand side is the notation for the subspace generated by the family Vi, and by definition this is, so by definition this is the smallest subspace of V containing all the elements Vi. So if any time one wants to check that somebody is a generating system for V, we need to check that V is the only subspace which contain all these guys. Okay. So the coefficients in this representation, the coefficients AIs in this linear combination, K linear combination, are in general not uniquely determined. For example, if X has another representation, summation bi vi, where the tuple bi is in k power I, round bracket I, is another representation as K linear combination, then 0 will be equal to x minus x, and when you collect the coefficients you can rewrite the difference as I in I, ai minus bi vi, which will be equal to ci vi. I am just calling ci equal to ai minus bi, I in I, and this will also be, ci will also be in k power round bracket I. If CIs were some CIs were non-zero, then you get a representation of 0 as a linear combination of VI, non-trivial. So if at all there is a different representation, then it leads to the following new definition. So the uniqueness of the coefficients ai demand the following condition on the family Vi. What condition? So that is, let me put it in the definition form. So definition, a family Vi, I in I, of elements in a vector space V is called linearly independent over K if the following holds. If ai is an I tuple which is in k power round bracket I, that is almost all ai's are 0, and if the linear combination ai vi is 0, then ai should be actually 0 tuple, ai equal to 0 for all I in I. If Vi, the family Vi satisfies this property, which we call it linear independence over A, then the uniqueness will automatically follow. We will say that family Vi, I in I, are linearly independent and linearly dependent if they are not linearly independent. So linearly dependent means, so that is, there exists an I tuple AI in K power 1 bracket I with the combination, the linear combination AI Vi is 0, I in I. There exists a not non-zero. This is non-zero tuple. Tuple is non-zero means at least one of the component is non-zero. So, if such a thing exists, then let I naught be in I be such that AI naught is non-zero. Then you multiply, you solve this equation. So you keep multiply this by AI naught inverse this is also 0 because this sum was 0 and you have multiplied this sum by AI naught inverse. AI naught inverse exists because AI naught 0 is non-zero element in the field and therefore inverse exists. And this one is now, I can write it as Vi naught plus the remaining guys. AI naught inverse AI Vi, this I in I and I different from I0, and I will transfer this sum to the other side. So then, so that will imply Vi naught equal to summation I in I naught equal to I naught. Coefficients are now AI naught inverse AI Vi. So that means the element I naught element in this family is a linear combination of the remaining ones. So that means in a generating set we don't need this Vi naught. So this is, so this says that, so therefore I will write a consequence, therefore a system of vectors, sometimes I call it vectors, sometimes I call it elements in a vector space. System of vectors is linearly independent if and only if no vector in this family can be expressed as linear combination of the remaining family, of the remaining vectors. Here, okay. In particular, if Vi family is linearly independent, then Vi cannot be equal to Vj if I is different from j. So in a linear, this means in a linearly independent family, no vector is repeated. Also the trivial remark, a family Vi I in I is linearly independent if and only if every finite subfamily V j, j in j, j is the finite subset of I. This finite family is linearly independent. So now going back to the earlier remark, if X is a linear combination AI Vi, I in I, AI in k power round bracket I, and the family Vi is linearly independent, then the tuple AI is uniquely determined by X. So this leads to the following definition. So definition: a family Vi I in I of vectors in a vector space V over K is called a basis of V if one Vi I in I is linearly independent over K. Over K is, sometimes I skip it when K is a fixed field and there is no way to confuse it, but it is a better habit to write it always. And 2 Vi I in I is a generating system. For V, that is V equal to the sum of the subspaces. This means every element of V has a representation of a k-linear combination among Vi. This is not Xi, Vi. Vi. So if Vi is a basis, so I continue on next page. If Vi I in I is a basis of V, then every vector x in V is a linear combination x equal to AI Vi, AI in the I tuple in the k power round bracket I, and the coefficients AI which are elements in the field are uniquely determined by x. There are only finitely, remember, there are only finitely many AIs could be non-zero. So in this case, for I in I, AI is called the ith coordinate of x with respect to the basis Vi. Sometimes these are also called ith components, but I will use ith coordinate. So that means, so to put it in a different way, so for each I in I, look at the functions from V to I, V to K. These I will denote, these functions depend on this given basis. So I will write it Vi star. This function is defined, arbitrary vector x in V goes to Vi star x, that is by definition it is AI. This makes sense because AIs are uniquely determined. So these functions are called coordinate functions. On V with respect to the basis Vi. Of course, we have not yet this. No, I should clean up a little bit. This is only one. For each I, Vi there. This is called ith coordinate function. So we have as many coordinate functions as there are basis elements. Of course, I have not yet addressed the question whether a arbitrary vector space has a basis or not. This is under the assumption that if it has a basis, then these definitions make sense. So in the next few lectures, I will also be concerned in general question if V has a basis or not, and if there are two bases of V, then what is the relation between their cardinalities. And we will prove that any two bases of V have the same cardinality, and this common cardinality will be called the dimension of V. Okay, but before I do that, I want to get used to these functions, etc. so on. So therefore, in this notation, each vector x, we can write it as linear combination of AIs, and this Vi star x Vi. Note that only finitely many coordinates of any vector x in V can be non-zero. So the only difference between this and this, I just wrote the value of that. These AIs I have replaced by VIX. So the reason being, you see the right hand side is also now it involves only a basis and X. When you look at this sum, one may wonder what is AI, how do you calculate AI? But if you write this expression, then it is clear from the way of writing that it is depends on X and this Vi. Okay. So moreover, these functions Vi coordinate functions. Vi star. These are functions on V with values in K, and they are as many as the number of basis elements. They are numbered by the same set, and they respect addition of V and scalar multiplication of V. So that is for all X and Y vectors in V, all scalar A in K, these two equations Vi star X plus Y equal to Vi star X plus Vi star Y and Vi star Ax equal to A times Vi star X. These two equations hold. That means this V, the first means V is an abelian group homomorphism. V plus is an abelian group, K plus is also an abelian group, and this first equation means it's abelian group homomorphism, and second equation means that it respects the scalar multiplication. That means whether I multiply by a scalar and apply a coordinate function, or I multiply a scalar later after applying the coordinate function. These two are same. So these in general, these are called K-linear maps. But more on just now I do not want to get into this because I still have to deduce some more consequences from the definition of a basis, etc. So I will come back to these one or two lectures little late. But right now I want to note what we have observed in the form of theorem. So theorem, let V be a vector space, V be a K vector space, and let Vi be a family of vectors in V. I want to translate all the definitions what we have defined so far: generating system, linear independence, and a basis in terms of the maps. So let from K power I round bracket I to V be the map defined by any I tuple here who has only finitely many non-zero entries. Map these to the combination AI Vi. This makes sense. This is a finite sum because this is an element here, and it's each tuple will uniquely determine this combination. Then these are the statements I am writing, they are merely the translations of the definitions that we have above. Number 1, Vi I in I is a generating system for V if and only if the map F is surjective. Surjective, let me just recall, surjective means every element of V is in the image of this map. I call this map as F. That was indeed the definition of a generating system. Second one, Vi, I in I, is linearly independent. Over K, if and only if F is injective. Injective means two different elements, they will have different images. So this is also clear because a linearly independent family and vector cannot have two different linear combinations. The coefficients are uniquely determined. Third one, combine 1 and 2 this side. So Vi, I in I is a basis of V if and only if F is a bijective map. Bijective means injective and surjective. Surjective and injective. So these are merely the restatements of the definitions. So from next time I want to consider many examples which will make these concepts more and more clearer. So thank you, till next time.